Learning objectives. In this chapter, the user would learn the following in detail: bisection method, iteration method, Newton-Raphson method. Bisection method. Bisection method is the simplest among all the numerical schemes to solve the transcendental equations. The scheme is based on the intermediate value theorem for continuous functions. This method is also known as bisection of Bolzano or interval halving. Bisection method. Once we have found an closed interval x1, x2 containing a root, we want to find a smaller interval containing the root so that modulus of x2 minus x1 less than or equal to epsilon for a chosen epsilon. Bisection method. This is done by computing f of x1 plus x2 divided by 2 and testing its sign against signs of f of x1 and f of x2, that is f of x1 plus x2 divided by 2 greater than 0. If f of x1 plus x2 divided by 2 and f of x2 and have the same sign, then the root must be in the closed interval x1 plus x2 divided by 2 comma x2. Otherwise, in closed interval x1 comma x1 plus x2 divided by 2. Bisection method. Thus, at the next stage, the interval of search is reduced to half its previous length. This method can continue halving intervals. Computational procedure. In this section, we describe an algorithm for computation of a root from a one-dimensional non-linear equation using the method of bisection. Computational procedure. To determine a root of f of x equal to 0 in the closed interval x1, x2, input the function f of x is equal to 0, error limit of the root epsilon, and the interval and the closed interval x1, x2, where f of x1 and f of x2 have opposite sign. Bisection method. Output root z. Step 1. In the closed interval input, read x1, x2, epsilon. Step 2. In the closed interval, compute midpoint of the interval. Then z is equal to x1 plus x2 divided by 2. Step 3. Squeeze interval. If f of z, f of x1 greater than 0, then x1 is equal to z, else x2 is equal to z. Computational procedure. Step 4. In the closed interval, looping for refinement, repeat step 2 to 3 until modulus of x1 minus x2 less than epsilon. Step 5. In the closed interval output, print the root z is equal to x1 plus x2 divided by 2. Step 6. In the closed interval, terminate the algorithm. Stop. The final value x1 plus x2 is usually accepted as approximation to the root. Note, if the given interval, that means it's a closed interval, x1, x2 does not obey the condition that f of x1 and f of x2 have opposite sign, then this algorithm fails to find a root. Computational procedure. Solve x cube plus 1.2 x square minus 4x minus 4.8 equal to 0 bisection method. Now we are going to solve the problem. First we have to find the between which numbers the root lies. F of x is equal to x cube plus 1.2 x square minus 4x minus 4.8 equal to 0. We putting x is equal to minus 1. If you put x is equal to minus 1, we getting f of minus 1 is equal to minus 0.6. Then f of minus 1.5 is equal to 0.525. Therefore, f of minus 1 into f of minus 1.5 less than minus 1 minus 1.5. So we taking x naught is equal to minus 1, x1 is equal to minus 1.5. Then x2 is equal to x0 plus x1 divided by 2. After substituting the values of x0 and x1, we are getting minus 1.225. Then we have to put this x2 in our f of x. After putting x2 is equal to minus 1.225 in our f of x, we are getting f of minus 1.225 is equal to 0.625. Again we putting f of minus 1 into f of minus 1.225, and again we getting less than 0. Therefore, x3 is equal to minus 1.113. We getting this minus 1.113 using our 1.225. Then f of minus 1.113 is equal to, we getting minus 0.2402. So that f of minus 1.113 into f of minus 1.225 is less than 0. Then x4 is equal to minus 1.169. Then f of minus 1.169 equal to minus 0.0816. So that f of minus 1.169 into f of minus 1.225 is less than 0. Then x5 is equal to, we getting minus 1.197, minus 1.197. Then f of minus 1.197 equal to minus 0.007. Then f of minus 1.197 into f of minus 1.225 is also less than 0. Then x6 is equal to minus 1.211. f of minus 1.211 is equal to 0.279. So that f of minus 1.197 into f of minus 1.211 is also less than 0. Then x7 equal to minus 1.204. Then f of minus 1.204 equal to, we are getting 0.0032. So that f of minus 1.197 into f of minus 1.211 is also less than 0. Therefore, we are getting x8 equal to minus 1.2005. Then f of minus 1.2005 equal to 0.003. Therefore, the root minus 1.2 correct to 3 decimal places of decision. So finally, we get the answer. How we know we get the answer means, in using x8, we getting f of minus 1.2005 is equal to 0.003, and then before this, preceding to it, x7 is equal to, we getting minus 1.204. Using that minus 1.204, we getting f of minus 1.204 is equal to 0.0032. f of x7 is equal to f of x8 equal to, we getting the more or less same answer. So we have to stop the problem. So we getting the same answer. Geometric interpretation. The f of x has a root between x1 and x2. Since function f of x intersects x-axis, the midpoint of x1 and x2 is z1. It is also observed that the function f of x intersects the x-axis in between x1 and z1. Geometric interpretation of bisectional method f of x. Again we find the midpoint z2 of x1 and z1 and observe that the function f of x intersects the x-axis in between z2 and z1. So we observe that after each bisection, the range of the interval is reduced and z approaches the point of intersection, that is root, from either sides of the range. General iterative method. Iterative methods are methods of successive, hopefully better, approximations to a root of an equation f of x equal to 0 may be described as follows. Let x1, x2, etc. up to xn plus 1 be n plus 1. Approximations to a root of f of x equal to 0. Let x is equal to xi. The information used may consist of the values of f and certain of its derivatives. Xi, xi minus 1, then finally etc. xi minus n. Xi plus 1 is equal to pi of xi, xi minus 1, etc. xi minus n. General iterative method. We call an iteration function if. The argument string of pi should also include symbols denoting values of f and its derivatives, since they may also be used in the computation xi plus 1 of. For simplicity, we never list these symbols explicitly. If xi plus 1 is equal to pi of xi, then pi is called a one-point iteration function. The process of iteration consists in generating a sequence of iterates x1, x2, etc. by the computing rule. A useful and successful iterative method must be such that the sequence of iterates converges to the root alpha. Let ei is equal to xi minus alpha. If there is a real number p and a non-zero constant c such that modulus of ei plus 1 less than or equal to c into modulus of ei power p for I is equal to 1 to etc. General iterative method. Then p is called the order of the method. It is to be noted that all iterative methods require one or more starting approximations to start the iterative procedure. Compute a real root from f of x equal to x cube minus 3x minus 5 equal to 0 using iterative method. Here we can rewrite x cube minus 3x minus 5 equal to 0 as x is equal to pi of x equal to square root of 3 plus 5 divided by x. Assume initial value of x is 2. The table shows the successive iterations for x cube minus 3x minus 5 equal to 0. Geometrical interpretation. The given function f of x equal to 0 is rewritten as x is equal to g of x. Now we observe that the root of f of x equal to 0 is the point of intersection between the curve y is equal to g of x and the line y is equal to x. The graph shows the curve y is equal to x. Initially, we choose an arbitrary root x is equal to x naught. Say, if the point x0, g of x0 does not lie on the line y is equal to x, then we choose another point x0, g of x0 and check if it is on the line or not. This process will continue. If this process converges, then its x coordinate tends to a root. Linear iterative method. The simple method is designed for equations of the type x equal to g of x, starting with a suitable approximation x0 to the root alpha. We compute xi plus 1 equal to g of xi for I is equal to 0, 1, 2, etc. and obtain the sequence x1, x2, x3, etc. If the sequence converges to alpha, then from xi plus 1 equal to g of xi, we have limit xi plus 1 equal to limit g of xi or alpha equal to g of alpha. This implies alpha is the root of x equal to g of x. Geometrical interpretation. The figure shows the point C of x0, y0 on the curve y is equal to f of x. We draw the tangent at C and find the point of intersection of this tangent with the x-axis. The x-coordinate of this point of intersection is given by xi plus 1 equal to xi minus f of xi divided by f dash of xi for I is equal to 0, 1, 2, etc., which is taken as the next approximation. So, the root is approached through such tangents successfully. Now, x0 minus f of x0 divided by f dash of x0 equal to OB minus BC divided by BC by AB equal to OB minus AB equal to OA plus XI. Here, the tangent as C is AC, where A is the point of intersection between the tangent AC and x-axis OX. Therefore, OB equal to x0, BC equal to y0 equal to f of x0, f dash of x0 equal to slope of the tangent equal to BC by AB from the right-angled ABC. Conclusion. In this chapter, we have covered the following in detail: bisection method, iteration method, Newton-Raphson method.